Good morning, students. Today our topic is graphical representation of a linear motion. We already know that for the objects in motion, two quantities are always changing. Those two quantities are position, or we can say the distance of the object, and time. Means if more time is elapsed, then we can say that the more distance is covered. Or sometimes during the motion, the speed may also change. That is, the object may cover longer distances in short intervals of time, or it may also cover less distance in long intervals of time. So now in talking we are saying so many things, but we want to represent this so by using the graphs. So for showing all these things we draw graphs. So a graph is a pictorial representation of two related quantities. Means, so we will draw graphs taking two things as a reference. So now for drawing graphs, what we need? So the main things that are required for representing are, first look at this example. I'm asking you, if I'm drawing this point here, if I ask what is the distance of this point, then how can we say the distance of this point? Means, or if I'm saying that in which direction does this point lies, so then we will not have the answer for this. So for talking about the position of something, we need something that is fixed, or we need some reference point or some point of observation. So that point is called as the origin. Now if I'm saying that this point is the origin, then we can measure this distance. Let us say that this is 1 meter, then I will say that this distance is 1 meter towards the right. Now towards my right, I'm saying now I cannot say that this distance is in which direction on the basis of east, west, north, south, or in terms of direction I will say now. So we have actually 6 directions. 6 direction means we already know this: east, west, north, south, and we need 2 more points, up and down. Means, so we have 6 directions. Or in Hindi or Punjabi we can say that आगे, पीछे, दाएं, बाएं, ऊपर और नीचे. So for example, so these directions can be represented by using 6 things. So for this I'm showing you this one system in which I have drawn this. So have a look at this. I have drawn, or I have taken one thing. So here I can say now, look at this. So now I will say that आगे, पीछे, दाएं, बाएं, ऊपर और यहाँ पे ये नीचे. Means east, west, north, south, up and down. So these are the 6 directions. Now it will become very difficult to draw these things on the paper, or we are using 6 directions. So in physics actually it was decided that we will be using only 3 terms, so that we say as x, y or z. Now once again I'm saying 6 directions, and I'm saying that this will be represented by these 3 variables. So means these 3 variables, why I am talking is, if I'm taking right as x, then left will be taken as minus x. If I'm saying in front, means आगे as y, then backward it will be minus y. And if I'm saying that upwards is z, then downward will be minus z. So with the help of these notations, means x, y and z, we can represent all the 6 directions. Or now, so to draw this, now I'm saying that the thing is, actually if I'm representing, or if something is east here, then it may also change if the position changes with respect to the globe, we can say that. So if something is towards my east here, it may be towards west for someone else. So for this, we are not talking about in terms of east, west, north, south, up and down, because in physics everything is fixed. So means if something is true here, then it should be true everywhere. So for this, we are taking x, y, and z. So if now I'm saying that this is the x direction, then this will be the minus x, and if I'm taking y here upward, and minus y will be downward. Now the third thing. So now I have looking at this now. So I have drawn this. I have also drawn this, but this is not possible to be drawn here. So for this, what we are doing is we are taking some system. So we can draw this as a dotted line, where I am drawing using this dotted line to represent this upward and downward direction. So now for taking the position now of something, so let us say that I'm taking one point here now. I'm saying that this is the point P about which I'm talking about. Then we can say that its distance from here, origin, or its displacement from here is this. But how much I've moved towards the x, then we can drop a perpendicular from here, and we can get the displacement towards x. And then if I'm dropping a perpendicular from here on this line, then from here I can get the displacement towards y. Similarly, on dropping some perpendicular on the z-axis, we can get the upward or downward value. So means these x, y, and z will be required for representation in 3 dimensions. But for the time being, means our linear motion, because we are always taking motion along a straight line, so mostly we will talk about the 2 directions only. Means so we will be taking 2 things, 2 axes, those will be perpendicular to both. So this is also called as a Cartesian system, because this was developed by Cartesian. So that this system is called as a Cartesian system, in which we are taking 2 axes perpendicular to each other. I'm representing this as x-axis, and this is the y-axis. So here in this plane now, every point has a address. Means if I'm locating one point here now, this point has a address. For finding that address, means how much we have to move towards right and how much we have to go upward on this plane. So if I'm saying that I'm moving x units towards the right and then y units upwards, then this point will have address that is represented by px comma y. This is called as the ordered pair, because we have already decided that the first value will be representing x and second value will be given by y. So now every point can be represented on this plane. Now origin is the must. Now second thing is, for graphical representation we need a table. We need a table. Means we have already seen this example. We are saying that some body is moving along a straight line, and at time 0 second, let us say that the position is also at 0 meters. Then let us say that after 1 minute, means if time is 1 second, then the object is at, let us say that now 10 meter. And if the time is 2 second, then let us say that the object is at 20 meter. And for time equal to 3 second, distance is 30 meter. Now in the tabular form, I can write this in this way now. One is time and one is position x. So when time was 0, the position was 0 meters. I'm saying the time will be in second and distance is in meter. So if time is 1 second, then the position is 10. If time is 2 seconds, then the position is 20. And if time is taken as 3, then the position is 30. Now how to represent this on the graph? So here, looking at this, once again 2 things are once again changing. If the body is changing its position, then time is also changing. So now for this, I'm taking one thing on the x-axis. I'm taking here as time, so that's why only I have not drawn on this side, left side. Or we can draw downward, because sometimes object may go away from us and it may also move towards us. So for that we will talk about later. So this is not required for the time, because we will always take origin or time 0 second as our point of observation. So I'm saying that the time is 0, then on the x-axis we have to take care of the scale, because we should draw in such a way that the values are always given on the plane. Means if values are very small, then we can increase the size of this time on the axis, or if the distances are too large, then also we can use the scale. Means here I'm taking 1 centimeter as 1 second, 2 centimeter as 2 seconds, 3 centimeter as 3 seconds, 4 as 4. Now if time is given in nanoseconds or smaller values, then also I will have say that this is 1 nanosecond, this is 2 nanosecond, and so on. So depending upon the values, we can change the scale. Similarly on the y-axis. Now here please don't get confused by this value. I'm saying that x is not a notation. This is simply in our representation. I'm taking on y-axis x because only it is moving always in the straight direction. So this may also be taken as the straight direction. So it is not a problem for this. So now this scale I'm taking now as 10 meters. So this is taken for the upward or downward or height basis. I'm taking this as 10 meter, this is as 20 meter, this is 30, and this is 40 meters. I'm saying that x is in meters. Now, so when the time is 0, then the distance is also 0. When time is 1 second, the body is at 10 meters. And when the time is 2 seconds, let us say that now the body is at 20 meters. And at 3 seconds, the body is at 3 meters. Now, what about the value if I say that what was the position of the object when it was at 1.5 second? So for this now, means we need the position at other durations also. Then what we do is we join all these points, and then now if I'm asking about 1.5 second, then from here I can go upward, it's perpendicular to this point. If it is reaching the graph here, then from here I will move towards the left. So from here I will get the value or the position of the object when the time was 1.5 second, or similarly at some other instance also we can get the position of the object from this graph. So means every point on this line now gives the position of the object. So therefore we can say that this graph is showing the relation between the two things. It is showing the relation between time and the displacement. And mostly here in our case of one dimensional motion on the x-axis, we will take x-axis as a time axis. So x-axis as a time axis will be taken, and on the y-axis we may take x, means we can take distance, we can take position, we can take displacement. All these things are the same only. Now we have to name this. The third thing that need to be given is the name now. So what about the name of this graph now? So this graph can be named as xt graph. It can also be named as position time graph, or this can also be said as displacement time graph. So we have to name also. So means for any graph, so we need the origin point, we need the table, and we also need the name to be given to the graph. So in this way we can draw the graphs. Now one more thing that I have to talk about, that is also very important in this case, that is the slope of the graph. That is the slope of a graph. So slope or ढलान. Look at this line now. I'm drawing one graph like this. I'm saying that somebody is, or some graph is like this, and one is like this. Now which will be having more slope? Then I will say that this graph is having more slope, means ढलान, तो इसकी ढलान ज़्यादा है. So this is having more slope. So now what is the difference between these two in terms of quantities? So now looking at this, we can say that the angle with this x-axis is less in this case and it is greater in this case. So now we can have an idea that the slope may be in terms of angle, but angle is not enough to describe the things. For example, from this same table I'm saying that this angle is 45 degree, and let us also say that I'm having some object like this, and this angle is 150, this angle is 150, then this angle is 150 but this angle is 45. Now which is having more slope? So then once again we will say that this line is having more slope than this line that was having an angle of 150 degree with the x-axis. So means we can say that only angle is not sufficient to talk about the slope. So therefore we are taking the help of trigonometry and we are taking tangent. means we are taking help of tan theta. If I'm now saying that this angle is theta, then the slope is given as tangent of this theta, tangent of angle, so that is represented by tan theta. We know that this value is perpendicular over base. Perpendicular over base means I'm saying that if some object is at this point now, then the slope will be this value. So this is the value of something that is on the y-axis, so it will be y, and this is the value on the x-axis. So it can be written in the form of coordinate of y-axis over coordinate of x-axis, or sometimes we say ordinate over abscissa in terms of mass, ordinate over abscissa. Now in our case that I was giving one example here in the last page. So we have drawn something like this. We said displacement is here on this line or x, and then time was taken on the x-axis. So in this case the slope will give us displacement over time. And now from this we can clearly see that why we need to talk about slope. So in this case means in the case of displacement and time graph, the slope will give us the value of velocity. Similarly, if some quantities are shown by some other things, for example, I'm saying that I have one more graph like this, in which I'm saying that this is force and this is acceleration. Then what about the slope of this graph? So here the slope will be equal to force perpendicular over base over acceleration. So I think that you already know that deceleration force is equal to mass multiply acceleration. So from here F over A will be equal to m. So slope in this case will give us mass. So slope here is equal to mass. So means if now I'm showing these two things, so it is once again, if this is object A, this is object B, and I'm showing that, and this is the slope of the one object A, and this is the slope for the another object, then clearly looking from these two we can simply say that which object is having more mass, so the object having more slope. So that's why we are talking about the slope. So for comparison purpose, these slopes are very beneficial. We can take the help of the thing. Similarly, in our case of displacement and time graph, if I'm saying that two bodies A and B, one is having slope like this, another is having slope like this, then whichever will be having the more velocity. So clearly we can say that velocity of object B is greater than velocity of object A. Similarly, in case I'm taking velocity on this axis and time on this axis, then the slope will be equal to velocity over time. So velocity over time gives us the acceleration. And for comparison purpose, once again, so the graph or the line having more slope will be having more acceleration in this case. So why it will be so? So look at this for a particular time. If I'm saying that at some time I'm drawing a line like this that is parallel to the y-axis. So this is the value of velocity of object A, and this will be the velocity of object B. If I'm saying that this was A and this was for B. Similarly, if this was the graph for displacement time, then at some particular time this will be the position of A and this will be the position of B. So since in this duration or in short duration here, this object have covered less displacement and this have covered more displacement. So here the displacement was less and here the displacement is more. So simply we can say that this is moving with the greater velocity. Similarly here also, if I'm saying that the velocity of this is VA and this is velocity VB, so here after some time this was the velocity of A object and this was the velocity of B object. So therefore acceleration of B will be given as VB over T, and acceleration of A will be equal to VA of T. So since these time are same, so therefore the object that is moving with more velocity will be having more acceleration. So this is the use of the slope. Now in our case, now sometimes it is also possible to calculate the slope between two time duration. Means let us say that I'm talking about some time here t1 and here the time is t2. Once again, if I'm talking about a displacement time graph, so means I'm taking x on this axis. So now looking at this, so here for at time t1 the displacement is given by x1, and at time t2 the displacement is given by x2. So here in this case the slope between t1 and t2. So it can be taken as the slope of this triangle. It can be taken as the slope of this triangle that I have drawn here. So here the slope, it will be y values of y-axis. So here on the y-axis I have taken x. So means this value, this one, this value will be x2 minus x1, and this time will be t2 minus t1. So in this way you can find the slope and you can talk about some quantities. Now one more thing is left, the case of uniform and non-uniform. So in case of uniform, as we have drawn the graph in on our previous page, we have drawn like this, a straight line. We said at time 1 second displacement was 10, at time 2 second displacement was 20, and time 3 second the displacement was 30, 10, 20, 30 meters, and here it is time in second, so 1, 2 and 3 second. So for the case of uniform, these differences means for the equal intervals of time, equal displacement is covered. Equal displacement is covered in equal intervals of time. So we will say that the object is moving with uniform velocity. So for this, let us have a look at the slope of this portion, or this or this. So in this case, this tan theta or slope will be equal to, this unit is 10 and this is 1. So slope is 10 over 1. Similarly, in the next case, I am saying that tan theta 2. Here I am taking theta 1 and here I am taking theta 2. So in this case also, once again now perpendicular. So here also this length is 10. So this will be 10 over, and time is 1. 2 minus 1, it will be 1. Similarly, in this case also, the slope here is also 10 over 3 minus 2. So that will be also, once looking at this, so in the case of uniform, the value of slope will be equal. So equal slope means we will always get a straight line for uniform motion. Then what about the case of non-uniform? So non-uniform will be the case when the slope will be not a straight line. Means in that case we may get the slope as this. So have a look at, in this case I'm saying that this is 1 second, this is 2 second, this is 3 second, and this is 4 second. Have a look at this now. So for 1 second, look at this small triangle now. Let us say that this is 3, this is 1, and let us say that this is 10. So now I'm completing this triangle. So this was 10, so this will be 7, and this is, I'm taking always 1 second. In this case now, let us say that this position is at 10, 20 and 25 I said. So then this will be 25 minus 7. So look at this now. Slope in the first case, slope in the first case is 3 over 1, and slope in the second case is equal to 7 over 1, and slope in the third case, it will be 25 minus 7, so that will be 18 over 1. So look at this slope, value of slope is always changing. So now we can say that this is not a uniform motion.